Okay, so in your solutions, you have 0.5 N sodium chloride and 0.05 N magnesium sulfate. Okay, and you want to calculate the osmotic pressures of this solution. So we know pi is equal to I times concentration times R times T. Okay, so you want to estimate pi at two different temperatures. One is 15 degrees C, which is 287 K. Yeah, pi at the 37 degrees C, which is 310 K. Okay, so difficult thing is actually here, right? If you estimate, if you can calculate I and C correctly, R that's 8.04, T is just here, then you calculate the number very easily. So how do you estimate your I and C? So here you want to make sure you know when this guy dissolves, okay, you're going to produce one sodium plus and one chloride minus. And here you're going to produce one magnesium 2 plus and one SO4 2 minus. So basically you know the I is equals to 2 for both cases, right? So then the total constant, this will be 2 times, for your sodium chloride is 0.5, okay? And for this guy will be 2 times 0.05. Okay, so your total concentration will be just 1.1 N. Okay, so that's the concentration. So here, when you do your calculation, you know for this one, you just put 1.1 times R times T. Okay, so here you decide what unit you want to use. Okay, so if you want to use ATN, you put 0.082. Okay, temperature of course is 287, and this gives you the answer of 25.99 ATM. Of course, we can use different R. Okay, just make sure you know what's the corresponding units, and it shows up correctly. Then it's okay. Okay, so here is the same equation, but T is 310. Okay, so the answer will be 27.98 ATM. So that's for question number 1. Okay, it's actually very simple. Okay. So for question number 2 is actually the freezing point lowering. Okay, so in the lecture, what we give you is actually negative XB is going to be equals to delta H freezing over R times 1 over T minus 1 over T star. Okay, and the T star here is actually your freezing point. Okay, so here I think during the lecture I did not mention that the delta T F is equals to a constant K times the concentration, right? It's Kf times your concentration. So this is actually written in your textbook, okay? But you can come to this from here. Okay, so how do you do that? So when you do this, this one can be written as T star minus T, and bottom will be T times your T star, right? So T star minus T is actually your delta T. This is actually your delta T. Okay? And T times T star, okay? These two is going to be very close to each other. So in your textbook, what you write is actually, you can just write it as T star squared, which is your freezing point temperature squared. Okay? Alright, so if you rewrite this, you get negative XB is going to be equals to delta H freezing times TF T star squared T star square on the type is actually times delta T. Okay. So this is actually your delta TF, right? Because freezing point lowering. So you can rearrange this so you can get delta TF is going to be equals to delta H freezing on the top is your R times T star square, okay, times your negative XP. Okay, so now you have this equation. Okay, and you can also substitute your XP with molality. Okay, so we say previously we said the XP is going to be equals to X1, which is your solvent, times your molecular weight of your solvent, times your molality of your solute. Okay? So, since it's actually a dilute solution, so your X1 is going to be very close to 1. Okay? So you can rearrange this, then you get delta TF is going to be equals to R over delta H freeze times T star square times M1 times your molality of your solute. Okay? So if you compare this term with this equation, okay, delta TX is the same on the left. You have the molality here, right? So this is actually your KF. Okay, so this space is your KF. Okay, and this is actually very easy to. You can, if you know the delta H freezing, okay, if you know the molecular weight of your solvent, you can estimate your KF automatically. Okay. But in this question too, it actually gives you the KF already, right? So you said the KF. So in your question two, it says your KF is equals to 1.86 K kilogram per mole. Okay. And then the M is going to be equals to, so what do you have? You have 0.1 M sodium chloride and 0.1 M calcium chloride. Okay, so you know the sodium chloride is a strong electrolyte. Once it dissolves, okay, you produce sodium plus and chloride minus. So the effective concentration is 0.2 M. Okay. How about your calcium chloride? Questions? So for your calcium chloride, you produce 1 Ca2 plus and 2 Cl minus, right? So effectively, you are going to have 0.3 M of your from your calcium chloride solution. So in total, you're going to have 0.5 M concentration. Okay? And with this in mind, then you know your delta TF will simply equals to this. KF is 1.86 K. Okay. So here, this is very important, okay? You know the unit of this guy is how many moles per kilogram, okay? You want to make sure your K has the same unit. Okay, if your K doesn't have this unit, then you can use M. Okay, if your K has a unit of molarity, then you need to convert this one into molarity. Then you do the calculation to estimate the delta TF. Alright? So pay close attention to the unit. So delta TF is going to be equals to 0.93. Therefore, the freezing point, okay, so the freezing point is going to equals to, original is 273, 0 degrees C, right? So the new freezing point will be plus or minus minus, okay? Make sure you know it's freezing point lowering. Okay, it must be lower. Okay, so don't just add 0.93, it's minus, okay? So this is going to give you 272.07. Okay, so that's for the question number 2. Alright, question number 3. Okay, so the solubility of a solid Z, okay, Vs, you dissolve in benzene at 298K, 298K, and 1 atm. Okay, and the solubility, okay, is 0.275. And the gamma is 0.676. Okay, for saturated solution. Okay, for saturated solution. Okay, so first, compute the standard Gibbs energies of solution of Z as in benzene solution. Okay. So once you see this, okay, you know this is actually at the standard condition, right? Once you see this saturated solution, you know this is actually at equilibrium. Okay? So once you know this is at equilibrium, then you know G equals G naught plus RT of A, right? G is equal to 0. So you know the delta G naught is going to be equal to negative RT natural log K, and you want to know this guy. Okay? So this at equilibrium, you're going to have this, right? And then otherwise your G is going to be equals to, in general, what we write is, we say the general form we always write is actually mu is equals to mu naught plus RT natural log A, okay? And we can also write A as, for your solute, A is equal to gamma times your molarity. Okay. Okay, so I think here we need to be a little bit more specific. Okay, so in general, the definition of A is actually gamma times your mole fraction. Right, that's the definition of A. But in reality, many of the time, because people always use the molarity when they describe the solution, so we also write this A equals to gamma as your molarity. Okay? So in this case, okay, apparently this question tells you I wanted to use mole fraction rather than the molarity because it gives you this rather than N2. Okay? So in this case, then you use this to express your K, to express your activity. Okay? And then you know it's actually at equilibrium, right? So your mu is equals to 0. So this is gone. This is 0. Okay? Therefore, your mu naught or the delta G naught is going to be equals to negative RT natural log gamma times your x. Okay? Alright, so it's going to be equal to negative 8.314 times 298 times natural log gamma is 0.676 times 0.275, and the answer will be 4.17 times 10 to the third joules. Okay? So let's say your delta G naught, okay? And the second question asks you, what is the equilibrium constant K? Okay, apparently your K is going to be equal to just this. Okay, because it's equilibrium, so the gamma x is actually your K. And if you calculate your K is going to equal to 0.1859. Right? So let's go question number 3. Okay, question number 4. Okay, you know, for every chemical potential, we can write this as T natural log gamma I xi. Okay. You want to show that Hi is going to equal to Hi naught minus RT squared. Partial natural log gamma I, partial T, a constant P, and M prime. Okay, so how should we get started? Okay, first we need to know the Hi is going to equal to mu I plus TSI. Okay, so this G is equals to H minus TS, right? So H is equals to G plus TS. Okay, so these are things we learned very early on, okay? Then we do know what is SI. So the SI is defined as negative partial mu I, partial T, a constant P, and M prime, okay? Because mu I equals to this. Okay, so basically this is actually, you do the derivative of this whole equations with respect to T. Okay, so if you do that, you're going to get, the first term will be negative partial mu I naught, partial T, a constant P, and N. Okay, so let's do your first term. The second term, okay, you have T here, okay, your gamma is also a function of temperature. So the second term, okay, to do it like separately, okay. So if you do a derivative with respect to this, then you are going to get R natural log gamma I xi, okay, plus, okay, there's a negative sign in the front, so this one should be negative here, okay, and the third thing is also negative here, okay. So if you do the derivative with respect to this, then you get R times RT partial natural log gamma I partial T, a constant P, and M prime. Okay. So since this is this whole thing is your SI, okay, you can put these things back to here. Okay. So what you're going to have will be so your HI is going to be equals to your mu I plus T times this whole term. Okay. So E will equal to T times your negative partial mu I naught, partial t, a constant p, and n prime. Okay? So that's the first term. Just move this outside. Okay? And then t times this, you get negative RT natural log gamma I xi. And then t times this term, you get negative RT squared partial natural gamma I partial t, a constant p, and n prime. Okay? And what you do is actually, so you know your mu I is going to equals to this. Okay, so you rewrite your mu I as mu I naught plus RT natural log gamma I xi minus t partial mu I naught partial t m prime minus RT natural log gamma I xi minus RT squared partial natural log gamma I partial t, a constant t, and n prime. Okay, so then you realize this and this is the same, so they cancel out. So you end up with mu I naught minus t times partial mu I naught partial t, constant p, n prime minus RT natural RT square partial natural gamma I partial t and constant p and n prime. Okay, so here is actually the key. Okay, partial mu partial t partial mu I naught partial t. This is actually your SI naught, right? So it's actually negative. This guy is your SI naught. So you know the first two things is actually basically mu I naught plus T SI naught. Okay? Minus RT squared partial natural log gamma I partial T constant P and n prime. And the first two terms is actually just your mu I. Right? We want to show, HI. It's just your HI. HI naught, actually. Minus RT squared partial natural log gamma I partial T and constant P and n prime. Okay? So derivation is actually quite simple. The only thing you need to know is actually the SI is the definition of SI is this. So you need to do the differentiative with respect to t first, okay, and put it back in. And then you need to know your mu I is going to equal to mu I naught plus RT natural gamma I xi. Okay, and you cancel these two terms. You need to recognize this is equal to your SI naught. And you need to recognize when you sum them all up, this equals to your HI naught. Okay, so that's all for number 4. Okay. All right. So last questions will be your question number 5. So number 5 is trying to ask if today you have two species mixed together. One is benzene, right? One's benzene, the other one is actually what's the other one? Dichlorobenzene. Okay. And you want you to estimate, it gives you some conditions and want you to estimate the molecular weight of dichlorobenzene. Okay. So, anyone have any questions? I don't. I forgot to take a picture of that. Okay, so I think the things they tell you is actually, okay, you have a certain amount of benzene and dichlorobenzene. Okay, mixed together. And then if you measure the boiling point, okay, of these two solutions. So benzene is actually the solute, right? Because it's smaller amount. And dichlorobenzene is actually your solvent. Okay, and you say if you have some solute. Okay, so benzene is a solute, dichlorobenzene is a solvent. Okay, so if you measure the boiling point of the solution, the delta, okay, the temperature, the boiling point change from 80.09, and then it increased to 80.6. Okay, so if you have a solute, the boiling point change from here to here. Okay, and it says the delta H vaporizations is going to be equal to 32 kilojoules. Okay, and it's asking for what is the molecular weight of your dichlorobenzene. Okay. So this question I feel like is somewhat not so ideal because it not directly tell you what is the molecular weight of benzene. Okay, so you need to know the molecular benzene is around 78. Okay, and then what else did he tell you? That's all right. That's all he tell you. So how do you actually solve this problem? Okay, so it actually comes from here. Yeah, right. Dichlorobenzene is actually the solvent. Benzene is actually the solvent. Okay, so this is reversed. 80.09 to 80.6. Okay. So the first thing you do is actually you contour this equation. Okay. Of course, here I say this is for the freezing point, right? You can make it become a delta TB by changing your delta H from freezing to vaporizations. Okay, and the T star becomes your boiling point. Okay, and one is actually the molecular weight of your solvent. Okay, and this is the molarity of your solute. All right. So delta TB is basically temperature difference between these two. Okay, so in this case, you know your delta TB is going to be equal to 0.51. Okay. Delta H is this. Delta H, the correlation is 32 kilojoules. Okay, your R is 8.314. Okay. Okay, so with this, then you know this, you know this, you know this, you know TB. You also know the molecule of your solvent. Then you can solve for your MD, right? So your MD is going to be equal to your delta TB times delta H, the relation divided by your R, and then times 1 of your TB squared times 1 of your molecular weight of your solvent. Okay, and 1. So delta TB is 0.51. Okay, delta H is 32 kilojoules. Okay, R is 8.314 times. The boiling point of benzene is here. Okay, so 80.9. 80.09 plus 273. Okay, calculate in Kelvin. So square of that times 1 of the molecular weight of your benzene is 78 grams per mole. You need to convert to the kilogram. Okay, so you put all these numbers in, you're going to get your NB is around 0.51